Riemann sum. Okay, so this is basically what we just did, except for it says to use n partitions, which takes it from, oh, I think I can do this too. What in the world are we doing here? This doesn't make sense, right? So let's think about what we just did with 8. How did you guys decide that the width of each rectangle was going to be 0.25? Good. So the width of that interval from 0 to 2, that was 2, right? And we divided it by 8, right? Well, we're not going to divide it by 8 this time. We still are going to have the width is going to be 2 minus 0, or just 2, right? But we don't have 8 partitions here, so we're going to divide it by n. Okay? And so that, of course, just gives us 2 over n. That's the width of each rectangle. So whatever n is, that's the width of it there. Let's think about what this would look like on a graph. I'm going to draw my graph here. So we're going from 0 to 2, and same graph as we had before. Make it a little bit bigger so we can see it. And so we are going to split this into n partitions. So I'm just going to obviously I've got to put a finite number of these here, but this could be any number here. So we're going to split, assume they're all even, although my marks are not very even here. So if the width of each rectangle is 2 over n, this first rectangle has the width of 2 over n, right? So from 0, that would be 2 over n. And then what would the next tick mark be? The width of this is 2 over n, right? So from here to here is 2 over n. So we've got to take 2 over n, and we've got to add 2 over n again, which that has common denominator, so that would just be 4 over n. And then what would the next tick mark be? 6 over n, and then 8 over n, and then I'm just going to put dot, dot, dot. Over here, when we get to 2, we would have, basically we would end up with 2n over n, right? Because that would give us 2 for that. If we wanted, we could think this one right here, it would be 2n minus 1 over n. Right. I think. Well, let's not even worry about it. Well, yeah, let's not even really worry about that one. I might have that wrong. We don't need that. So, if we are going to do a Riemann sum for this, the width of each rectangle is 2 over n, so 2 over n would be out front, right? And then, if we're doing, it says to use a right Riemann sum, and there's a reason why we're going to use the right Riemann sum. It just makes it just a little bit easier to do. So the right Riemann sum, if I'm using the right Riemann sum, I do not use that first endpoint. I would use 2 over n here. So I would have f of 2 over n plus f of 4 over n plus f of 6 over n plus, I'm going to put dot, 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 and then my last one would be f of 2n over n. So, all of this adding this up over and over again, that sure looks like I could use it sure looks like I could use a summation for it, right? Especially since I've got this in, so I can't actually get a number for it. I can't plug those numbers in. So if I'm going to do a summation, the 2 over n, it can stay out front. I'm going to do a summation, and I've got to think about what I've got to do here. I guess I could have, instead of writing this, I could have done 2 over n squared plus 4 over n squared plus 6 over n squared plus 2n over n squared. Now here's my problem. Whenever we're trying to write sums for this, we look at what changes, and so you can see pretty easily the number that's changing is that top number. So I'm going to have in my Riemann sum, or my sum here, I'm going to have something over n squared. Here's the problem. Does it increase by an integer each time? Does it just go up 1, 2, 3, 4, 5, 6? It does not. We've got even numbers here. So I can't just put the I up here, because if I put the I would have 1 over n squared, 2 over n squared, 3 over n squared, 4 over. Even if I started at 2 over n squared, but then I have 3 over n squared, 4 over n squared, 5 over n squared. How could I make this 2, 4, 6, 8 instead of just 1, 2, 3, 4? Any ideas? Okay. Okay, so like I plus 2 over n, like that. Alright, so if we were doing the sum, let's say it started at 1. So if I plugged in 1, I'd have 1 plus 2 over n, which would give me 3 over n. Would that work? But I could do 2i, right? That would give, so if I do that, so that was a good idea on that one, but it didn't quite work. 2i over n, so that'd be 2 times 1 over n, and then 2 times 2 over n, and then 2 times 3 over n, which would give us 2 over n, 4 over n, 6 over n, and so forth. So if you need even numbers, which happens a lot, use 2i, because 2i will give you only even numbers. So we will go from I equals 1 to n of 2i over n squared. Okay, so here is where your shortcut rules from last night have to come in. So many of you, I think, as I was looking, probably did it the long way because the shortcut rules are a little bit confusing. But here is where they come in and where they have to be used. Because n is my number of rectangles. We talked about this the other day. One way that we can make our predictions better is that we can use more and more and more and more and more rectangles, right? If we use 2 rectangles, it's probably going to be a pretty bad estimation. If we use 4, it would be better. If we use 8, it would be even better. If we use 100, it'd be pretty close to what we actually need. But what did we say was the number of rectangles we wanted to use to get the exact amount? Infinity, right? If we could use infinite rectangles, then we would get the exact area underneath the curve. So n is my number of rectangles. So what if I take this expression right here and I do the limit as n approaches infinity of this stuff here? If I do that, it will give me the exact area underneath that curve. Okay, so this is where our shortcut rules come in, because I can't do this limit whenever I've got this stuff right here. So we have to use shortcut rules for this part. So I'm going to sort of do that to the side and then we'll come back to this. So for this sum of from 1 to n of 2i over n squared, I'm going to go ahead and square everything. So it's going to be 4i squared over n squared. And what could we pull out front out of this, that 4i squared over n squared? 4 over n squared could be pulled out front. And so that would be 4 over n squared of I squared. If you look back at your notes from yesterday, which I don't blame you if you've got to keep close by because I still have to keep close by, we had a shortcut rule for this. And that shortcut rule was, it doesn't look much like it's n times n plus 1 times 2n plus 1 all over 3n squared. And whenever we replace that, the summation is gone. Okay, so what I should have kept this all separate. This right here was just the stuff in the red box. Okay, questions on that part? Alright, so what we can find now, I'm going to go up here, is the limit as n approaches infinity of 2 over n times 4 over n times n plus 1 times 2n plus 1 all over 3n squared. I'm sorry, I lost the square right there. 4n squared. Hold on, I think I've done something wrong. I have. I was. This is not 3n squared. It's a 6. That's a 6. I was looking at the next step of the problem. There. It would help if I knew my shortcut rules better, but I don't need to know them. Okay. So over here, this would be 8 over n to the third. Up here, I think I'll multiply these two together first. So you've got 2n squared. You'll have plus n plus 2n, so you get plus 3n plus 1 over 6. Don't lose your limit notation. And so we'll have 8 over n cubed times 2n to the third plus 3n squared plus n all over 6. And then if we just multiply top and bottom, we'll distribute this 8 right here. So limit as n approaches infinity of 16n to the third plus 24n squared plus 8n all over 6n to the third. It might be helpful as you do this homework just to remember that n times n plus 1 times n 2n plus 1 equals 2n to the third plus 3n squared plus n, just to save you a little time for multiplying that out. And so when we look at this, now we've got a limit as n approaches infinity of an expression with n, so we know how to do this. What do we do whenever we have a limit as n approaches infinity? It's been a really long time since we did those problems. Good. So everything gets divided by the n cubed. And so the n cubed cancels here. Right here you get 1 over n. Right here you get 1 over n squared. What happens to anything that has an n in the denominator? Becomes 0, so this is gone, and this is gone, and we just end up with 16 over 6, or that will reduce to 8/3. Okay, this is the exact area underneath the curve. Also on that, you can do Bobo-Botno, each CC right there. Exponents are the same, divide coefficients. Probably, if you're asked to do this on the AP exam, you're probably not going to be asked to do this on a free response, but if you were, I don't think they would care if you don't show work on finding that last step, so Bobo-Botno would be okay. Alright, so that is the exact area. So 8/3 is what, 2.6 repeating? Yes. So our estimates, we had 2.18, 3.187, so we're between those two there. But this is the exact area, which is going to be important for us moving forward, because why would we want to know just an estimate if we could find the exact area, right? So we are going to be using this more. Yes. The 2 over n part right here. Okay, that 2 over n is the width of each rectangle. So you're doing the width of each rectangle is 2 over n. So like whenever it was 8, we were doing 2 over 8, which gave us 0.25. But n's our number of rectangles. If we only have 4 rectangles, it'd be 2 over 4, which would be 1/2. If we had 100 rectangles, it'd be 2 over 100, which would give us 0.02 there. So n's your number of rectangles. So it's the length of your interval divided by the number of rectangles. And so that has to be the width, and then you multiply by the stuff here. I kind of left that out for a minute while we worked on this stuff, but then included it back in whenever we did this here. Okay, questions? All right, now the next one asks us to do this with a left Riemann sum. So if we were to do a left Riemann sum, we would still have 2 over n. But instead of multiplying by, instead of doing f of 2 over n, we would have to do f of 0 first, right? And so what we would have here is we would have, I'm going to use 0 squared plus 2 over n squared plus 4 over n squared plus 6 over n squared plus dot, dot, dot. And then we wouldn't end up at 2. We would end up at 2 times, I think it's 2 times n minus 1 over 2, I believe. There. It's really not all that important what you got right there. It'd be the number right before your n. So if I tried to write this using summation notation, I would have 2 over n. I would have the sum. This time, I could still do the same sum, the 2i over n squared, right? Because I've got even numbers here, so that 2i over n, that'll count up by even numbers. But what should my I start at if I do this? 0, 2, and instead of going all the way to n, I go to n minus 1. Okay, I am not going to go further with this. This is how you would set this up. But the problem with this is shortcut rules. Only work for I equals 1. So since shortcut rules only work for I equals 1, that means that it is going to be much more difficult for us to use this particular rule right here. So the moral of the story here is right sums are easier. You see them? Okay, so your right sums are easier to use in this case. So left can be done, but we don't have shortcut rules for this, so I think we could do it in the calculator. Let's see if the calculator will do it for us. You could do the limit. How do I do this? I have to do the limit of 2 over x times the sum. I'm just curious to see if this will work. Of 2x. You have to use n's and x's. N's and i's here. Okay. Let's not do it. We don't have enough time to do that. But I think the calculator will do it. But it just won't be easy. So right sums are typically going to be easier. So the limit definition of the area of a region in the plane is the limit as n approaches infinity from 1 to n of f of ci. This right here is your f of n 2 over n, f of 3 over n, f of 4 over n, f of 5 over n, 6 over n, all that stuff, times delta x. This delta x right here, that is your width of your rectangle. And your width of the rectangle is b minus a over n. So b minus a over n, that is like on the last problem we just did 2 minus 0 over n for that. Okay, questions? Okay, let's try another one. Let me do that. Okay, so we're going to find the area of the region between the graph of the function f of x equals 4x plus 2 and the x-axis over the interval 0 to 4. So this time our delta x, our width of our rectangle, it would be 4 minus 0 over n, or 4 over n. So when we're thinking of, I'm not going to graph this completely, but when we're thinking about that graph, we'd have 0, then we'd have 4 over n, and then we'd have 8 over n, and then we'd have 12 over n, dot, 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 all the way till we got over here to 4n over n. So if we are finding the area here, we would do the limit as n approaches infinity of delta x, which is our width of our rectangle, which is 4 over n, times the sum. Actually, no, let's not do the sum yet. Let's do this. Let's do f of, we need to count by, we're going to use the right hand sum, so it'll be 4 over n plus 8 over n plus 12 over n and dot, dot, dot there. Which, if we actually plug into the equation, would look like this. Over n times, so we'd have 4 times 4 over n plus 2 plus 4 times 8 over n plus 2 plus 4 times 12 over n plus 2 plus dot 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 there. And you don't necessarily have to write any of the stuff I'm writing right now every time. It helps me see what is changing each time. And so when we look at this, we've got a 4 and then an 8 and then a 12. So if we're writing this as a sum, we've got the limit as n approaches infinity of 4 over n, and then we're going to write the sum from 1 to n of 4 times something over n plus 2. And what is that something that we're going to put over n? Okay, close. If it were 2i over n, then when I plug in 1, I'd get 2 over n, and then when I plug in 2, I'd get 4 over n. So in this case, we need to be counting up by 4s. So in this case, we're going to put 4i right there. And if we do that, then we'll have 4 times 1, which will be 4. 4 times 2, which will be 8. 4 times 3, which will be 12. And so on. So, for the sum right here, I'm going to write it, well, this could be written as, this is 4 over 1, so it could be 16i over n plus 2, and I could take the sum of each one separately. Okay, so if I do that for this part, I'll get 16 over n times the sum from 1 to n of I plus the sum from 1 to n of 2. And so that gets us down to where we've got the sum from 1 to n of I, which we have a shortcut rule for. And we have the sum from 1 to n of 2, which we also have a rule for because that's a constant. So limit as n approaches infinity of 4 over n times 16 over n. Shortcut rule for this one is n times n plus 1 over 2. And then shortcut rule for a constant is just 2 times n. So I'm going to reduce that 16 and that 2 and just make that 8. And then so if you distribute that 8n, we have 8n squared plus 8n over n plus 2n. And limit as n approaches infinity. Let's get common denominators here on top and bottom. And so if we distribute here, we get oh no, let's see, let's put that, this would be, right here, we'd have 10n squared plus 8n, that would be that part right there. So, we've got 4 over n. So we would have 40 n squared plus 32n over n squared. And then this is limit as n approaches infinity. To do our limit as n approaches infinity, we're going to have Bobo-Botno for this case. So what do we get for our answer? 40. So 40 is the answer. Now, I just made you do this whole thing. If you actually get this question on a test, don't do this. Because this is 4x plus 2. So you got a y-intercept at 2. You got a slope of 4. Not really gave myself enough room. It is a straight line from 0 to 4. This makes a shape you can find the area of. So graph it and find the area in the real case, because it would be a lot easier than what we just did here. Main thing is I wanted something that was fairly simple for us to do as far as the solving goes, because if I give you something like 87x to the third minus 42x plus 7, it can be done this way, but it would take forever to do. Okay, questions? Alright, so some notation that I need to introduce you to, and this will help you when you get to the last free response question on your problems for this week. And I'm going to give you just a hint on those towards the end. So a definite integral notation is something that you have not seen before, and it's my favorite math symbol. It's just so pretty. Look how cute it is. Just that. I've got some earrings that are integral symbols, and I meant to wear them today since it was the first time we've seen this symbol, but I forgot them. I'll try to wear them tomorrow. But this symbol right here, it's your this is a definite integral, and you've got the integral from a to b of f of x with respect to x is how we read that. And what it means is when you see that symbol, it is the area under the curve of f of x on the interval from a to b. Okay? And a is called your lower limit of integration. And the process of integrating is finding that area underneath the curve. And b is the upper limit of integration. And f of x, which is your function, we call it the integrand. And the integrand is what you are integrating. And integrating is finding the area under the curve. So you will definitely see this notation some if you look at the solutions that I posted to the last problem. When you see something like if I write from 3 to 6 of f of x dx, that means the area under the curve from 3 to 6. So it's sort of a shortcut of writing out that long written words, and it also we're going to do more with it as far as the notation goes as well eventually, but that's what that means when you see it on the solutions. So if we see a problem like this, the integral from -1 to 1 of 1 minus x squared dx. Okay, this means the area underneath the curve from -1 to +1 of 1 minus x squared. Okay, now I'm just going to do just a quick little graph of this for an important reason. If I graph this, we've got a quadratic here, 1 minus x squared, so this has been flipped upside down and moved up 1, so the graph will look like this. So we're looking for this area underneath this curve. Now, what do you notice about the two sides of that graph? They're equal to each other, right? So, what if we did this? What if we did this? What if we just found the area under the curve from 0 to 1 of 1 minus x squared? And what if we just doubled it? Would that work? That would give us the same value, right? It is going to be a little bit easier if you do that, because it is always easier if this number right here is 0. If your lower limit of integration is 0, it just makes the problem a lot easier to do. I am pretty sure that all of them that I am going to give you tonight for homework all have a lower limit of integration as 0, or you can do what I'm doing here, where you, because it's symmetric, you could just find the half of the area under the curve and double it. So let's do this. So if we do this, we're only looking from 0 to 1. So whenever I split this up on the x-axis, that first little tick mark, it would be 1 over n. And then the next one would be 2 over n. And then 3 over n. And so on until you finally get to 1n over n. There. So if I think of what I would have here, is it okay with you guys if we kind of, this 2 right here, let's hold off on it just so I don't have more numbers. We're just going to wait till the very end. We'll double our answer. So for this, I would have the width of each rectangle would be 1 over n. And I would be multiplying by 1 minus 1 over n squared. Plus 1 minus 2 over n squared. Plus 1 minus 3 over n squared. And so on. So if I write that as a sum here, it would be the sum from 1 to n of 1 minus, the number that's changing right here is 1, 2, 3. Now this one is counting up just by ones. So I could just put I over n squared like that. And so if I want to find the, actually I'm just going to keep going. I'm not going to even write the limit notation yet just because I don't want to take too long. So I could do the sum of these two things separately. So this could be the sum from 1 to n of 1 minus the sum from 1 to n of I squared over n squared. And the sum from 1 to n of 1 is just 1 times n. The sum here, this n squared, I could pull out front, which would be 1 over n squared times the sum from 1 to n of I squared. minus 1 over n squared times, and then this part right here, the sum from 1 to n of I squared, that's the shortcut rule, and it is n times n plus 1 times 2n plus 1 all over 6. And I said for us to remember what that equaled. What was it? It was 2n to the third plus 3n squared plus n over 6 . So that would be 1 over n times n minus 2n to the third plus 3n squared plus n over 6n squared. And let's get common denominators here. So this would have to be n squared. Oh no, you have to do 6. Yeah, let's do 6. 6n squared, so that'd have to multiply by 6 and n squared. So 1 over n times 6n cubed. That negative has to be distributed to everything here, so minus 2n cubed minus 3n squared minus n, minus n all over 6n squared. Don't worry, you don't have too many of these. 4n cubed minus 3n squared minus n over 6n squared. And finally, we will get 4n cubed minus 3n squared minus n over 6n cubed. And when we get that, we need to do the limit as n approaches infinity of all that stuff. What do we get whenever we do? We will get 2/3 for that. 4 over 6, which gives us 2/3. But that's not our answer because we have to multiply it by 2. So 2 times 2/3, because this was only from 0 to 1, gives us 4/3 would be our answer. Okay, questions? All right, the homework assignment is going to be page 347, 49, 50, and 54. And let me look through those, make sure those are all ones we can do. Let's make sure. Okay, so I only gave you ones that have a lower limit of immigration of 0 because they get really complicated when it's not 0. Although our progress check has some on them that are not 0. I'm thinking about skipping it and moving on. But so you've just got these 4. They do take a little while to do, as you have